Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. In the previous session, we started talking about stochastic processes. We said that a stochastic process is a mathematical formalism that we use to model mathematically an empirical process that changes dynamically with time. So, stochastic process can be defined as a family of indexed random variables. And in that previous session, we classified stochastic processes according to the index according to which the stochastic process is indexed, and also what possible state it can take. So for both the index and the state, we said that it may take on a discrete value or a continuous value. And accordingly, we classified the stochastic processes into 4 classes. Today we are going to talk about stochastic process from another viewpoint. So we need to see that stochastic process is no longer just a single random variable which represents the outcome of a single random experiment. It is a family of random variables, and because of that, like in a normal family, the members of a family are related to each other. The question then is, how are the different random variables that are part of this family of random variables associated with each other? In simple terms, what we are actually interested in is that how much back into the history is our process affected by. So for example, I am in a current state. Let's say a stochastic process is in a current state, and we have to decide what would be the next state. But then, is it only a function of my current state, or is it independent of all the previous history, or does it depend on all of the previous history? So these are the questions we would ask ourselves when we categorize stochastic processes by their dependence on each other. So that would be the first thing we will cover today, and then bulk of this session would focus on common stochastic processes, and we will see that we will focus on stochastic processes that are tractable, by which I mean that they are simple to analyze, and that actually has to deal with the first part of dependence between random variables. We will see that if all the random variables are associated with all the other random variables, it becomes very hard to analyze such a process mathematically. But luckily for us and for network performance evaluation, many practical processes can be modeled by simpler processes in which the dependence is of a limited nature. So this is the view of classical stochastic processes. But as mentioned during our lectures on fractals and on long-range dependence, all of these models may not be a very accurate depiction of how computer networks really are. So we would study these stochastic processes as models of network performance evaluation systems, but all the while we would keep in our mind that these are only approximations, and our actual world does not necessarily exactly replicate what we would get from our analysis. But if the models are good enough, then our approximations would be also good. So let's start now with the first part of today's session, which is we want to classify stochastic processes according to the dependence between the different random variables. So for that, we need to first of all study and refresh our concepts of how can we quantify dependence between, let's say, 2 random variables, and then we extend this concept to multiple random variables. And then if we have the tools available with us, we can then talk about quantifying the dependence between random variables that are part of a stochastic process. So the tool that we have for this is known as the joint distribution function. So if we want a probabilistic model for the outcome of a single random experiment, that is the probability distribution function. For the discrete case, this will be the PMF, the probability mass function. For the continuous case, this will be the probability density function. But now we are interested in not only seeing what value a single random variable would take, but now we are interested in seeing how we can study the dependence of multiple random variables and what is the probability of two random variables taking values that we specify. So to understand that, let us consider an example through which I will build intuition for joint probability, for conditional probability, and for marginal probability. So we are going to consider a very simple example. We consider the distribution of faculty members at various departments of a university, and we are only going to focus on two departments, the math department and the English department. Let's say we have some data for this, for some actual university, and the data that we have is shown on the slide. You see that in the math department, the male faculty members outnumbered the female faculty members by a long way. So total of 38 faculty members, there are 37 male faculty members and just a single female faculty member. But in the English department, we have both the male and female more or less on equal footing. So female faculty members are 17 and male are 20. So imagine that we abstract this thing. We think of these faculty members as two colored balls in an urn, and we want to take out a ball from the urn and we want to observe what are the chances that this is, let's say, a red ball. What is the chance that this is a blue ball? So the idea still is that you have a whole possible distribution of female faculty members and male faculty members, and from this population we sample, and basically we're asking the question, what is the probability that we are going to sample this particular faculty member? And we may be interested in seeing what is the probability of a female faculty member who works in the English department. So now if we have two conditions, then this would be a joint probability calculation. To understand this and to develop this example further, we will now change the numbers into proportions of totals. So we would just transform the data such that now we have relative numbers. So now you have proportions available, where if we count all of them, they would total to 1. And then you would say that the probability of a faculty member randomly chosen from the population of all faculty members at this university, the probability that faculty member would be teaching in maths would be the joint probability of faculty member being in math, and the other probability is that faculty member being male. So in this case, that would be 0.494, because that is the intersection of these two things. And similarly, we have the joint probability of being a female and being in the math department. As you can see, that is in our example very low. What is the joint probability that we would have a female faculty member who teaches in the English department? So this comes out to be 0.227. So we have the other joint probabilities given as well. Now let us study the concept of conditional and marginal distribution as well. So the question we ask now is not that we are sampling from the entire population and we have no information. The question now is that given the faculty member belongs to the math department, so this is thing which is given to us, this is prior information. If we have this information, now what is the probability of the faculty member being male? So I would like to emphasize, so that this becomes very clear, that we could have asked this question earlier as well, that we are sampling from a population. What is the probability of the faculty member being male? We are asking the same question, that what is the probability of the faculty member being male? But now we have more information. We already know that this faculty member belongs to the math department. And now this drastically changes everything. Because now we have some information and we can condition our probability expectation on the basis of that. So we can then gray out the area that is not relevant to us. And now the total population is not represented by 1, a probability of 1. The total that we are sampling from is 0.506, and the probability of a male chosen from this proportion of the entire space is 0.493. So now it becomes apparent that the probability of the faculty member being male, given that he belongs to the math department, would increase substantially, because there are almost all of the faculty members there are male. There is only a single faculty member who is female. We can see the joint probabilities now. The probability of a female math faculty member is just 0.013. The probability of a male math teacher is 0.493. The probability of being in the math department is 0.506. But this was if we did not know it. Now we already know it. So this then would be changed, and if we want to calculate the probability of male given being in math, the ratio would be 0.493 divided by 0.506. And this is almost 97%. So this gives us the intuition that now 0.493 would not be divided by 1. It would be divided by 0.506. Let's just now formalize this. What we are trying to calculate here is the conditional probability. Probability of male given this person is in the maths department. This is a conditional probability. This is a ratio of the joint probability and the marginal probability. If you observe closely, marginal probability is what we have been calculating in the margins. So for example, if I ask the question that from the total population, what is the probability that faculty member would be in the maths department? So that would be 0.506, because that is in the margin of the first column. What is the probability of a faculty member randomly chosen from the entire population? He or she belongs to the English department. That is 0.494. Accordingly, we can have marginal probabilities for being female, for being male, and so on. So if you observe closely, this P of maths here is just what we've already covered as the probability mass function. When we talk in the context of joint distributions and in the context of multiple random variables, we now call this a marginal distribution, but they are essentially the same thing. So from this entire example, I want to basically bring forth that conditional probability is not the same as joint probability. In joint probability, we are not told anything. We are going to ask ourselves, what is the probability that if we sample from the population of entire faculty members, our sample is both male and also he belongs to the maths department? That is a totally different probability from the probability that we will calculate given that the faculty member is already in the maths department. And what is the question asked to us? That given this, calculate the probability of being male. I hope the point has been clarified. So let's formalize this. In the previous example, we saw that conditional probability is the ratio of the joint probability and the marginal probability. Now, accordingly, if we just make some shuffling around, we would see that the joint distribution can now be stated to be the product of the marginal distribution and the conditional distribution. And that is what you can see on the slide now. Also, kindly see the notation. The probability of capital XY in the subscript within brackets X and Y tells us the joint probability of X taking a value of small x, capital Y taking a value of small y, in the case of discrete random variables X and Y. So this thing, the joint distribution, is equal to a product of the marginal distribution, and then there is a conditional distribution. This is simple to understand if we try to get the intuition of this. The question is, if we forget the formalism and the formula, the question is, what is the probability that we would have values equal to x and y? So that would be the probability of y and the conditional probability of x dependent on y. So we can work with one random variable at a time. That would be the marginal distribution. And then, given the probability of that happening, we can condition on the basis of this. So we've talked of joint distribution. I must highlight here that joint distribution is a complete description of a stochastic process. In other words, we see a sample stochastic process. We could have a different stochastic process because we are imagining this stochastic process to be just a sample from all possible functions that could have eventually resulted. So in effect, we are thinking of a generative model which is in a way creating a sample function and giving it to you. So because this is a random process, the chances of that happening is some given probability, and you would also have the chance of other functions being emitted by this generative model. So how do we quantify or characterize this generative model? We do that by specifying the joint distribution. In other words, we imagine that there is a process that is creating functions according to this joint distribution. And then the thing that we observe is just a sample from that. So these are very important concepts, the joint distribution and conditional distribution. And these are also slippery concepts because it is easy to confuse. So I would advise you to work on this very carefully and make sure that you know the difference between the two. Joint distribution for two random variables would be two happening without knowledge of anything happening. Conditional of one being conditioned on the other is that the first thing has happened and now you're interested in seeing the second thing happening subject to the given information. So why are we interested in doing all this joint distribution and conditional distribution? Because we want to model the dependence amongst the random variables in a stochastic process. If we want to model the entire stochastic process, we would need to define its joint distribution for all x's and y's and all time. And that is a formidable task, a very difficult task. Luckily, many processes are simple in the sense that every random variable is not dependent on all other random variables. In other words, the next state is not a function of the entire history. We can actually forget some of the history and still be able to work with it. So that is why we are actually able to work with more simpler models. So one other thing that we can highlight here, which follows from the joint distribution, is the concept of stationarity. If we have a stationary process, that basically tells us that if you observe the process at any given time, it is going to have the same statistical properties. It is not going to be the same, but it will have the same statistical properties. ये उसी तरह है कि अगर हम random variable consider करें और हम एक distribution से random variable sample कर रहे हैं, every time we sample, we are going to have a different value. But in the long run, it would actually be coming from the same distribution, and therefore the statistical properties would not change. When we have a stationary process, the statistical properties that define the entire stochastic process do not change. And that is very good for us because it makes analysis very simple. And stationarity is a difficult thing to prove. So it is an assumption, and we often make it to simplify our analysis. To highlight some processes that are not stationary, please have a look at the slide now. You would see that the first process is not stationary, because if we keep on having more samples, the mean is increasing. So if we start observing now, and if we start observing sometime later, your sample mean would be different, because the statistical properties that is generating this process is changing with time. So that is something that is non-stationary. You can also think of variance being reduced as the time moves on. So in other words, if the process is changing in its statistical character, we say that the process is non-stationary. And only if the statistical properties remain the same would we say that the process is stationary. Now we can talk about the dependence of stochastic processes, the dependence between various random variables. The simplest possible random process is one in which the random variables do not have any relation with each other. Every one is independent of all the others. So if there are discrete time observations, you would have a value that comes out of it that is independent from all the history. As an example, we can think of a Bernoulli random process. So you are maybe doing a coin toss in which a heads is a 1 and a tails is a 0, and you do this at discrete points in time. Let's say every day in the morning you toss a coin, and you do this for many days. So if you graph this is a stochastic process, because this is a family of random variables indexed by time. But knowing what happened today does not tell us anything about what will happen tomorrow and for the future occurrences. Even if we know all of the previous history, all the random variables from previous observations, it would not tell us anything about the current observation. So this is the IID stochastic process. The word IID refers to it being independent and also identically distributed. Every trial or every observation has the same distribution. So we can imagine that there is some distribution that we are sampling from, and it is independent. So just like in the case of a coin toss, what happens now is not going to affect what happens in the future. The future state is independent of all the history. While this is very good from the analysis perspective, it's not very good from the perspective of power to model real applications, because real applications often have memory and they depend on the history. So it's not that the future state is independent of everything that has happened. If we place this restriction, we would be able to model very few things. But in real life, many stochastic processes have some dependence. What the current state is now depends on the future state, the state on the future observation. So this then limits the utility of an IID stochastic process. And in fact, many people say that IID stochastic process is even a stretching of terminology, in that there is no structure in this stochastic process. This is just a repetition of the same experiment again and again. So to make things more interesting, we consider the concept of dependence. So again, the question then arises, how much dependence can we afford? And obviously the least that you can make do with and that works well for modeling would be good for you, because having dependence on previous history makes things difficult for you. Analysis becomes hard and you have to keep track of so many things. So we would like that you have some memory, because real life processes have memory. But we do not want infinite memory in that everything in the history affects us. So accordingly, let's have a look to study this dependence property and our need to have memoryless dependence. We use the concept of conditional distribution. Let me now tell you what memoryless means. Memoryless tells us that a process does not remember the trajectory it has come through to the current state. It forgets everything about the past. it knows where it is at. If the future state is only dependent on the current state, we would say that this process is memoryless. If the trajectory of the future path is dependent on the history as well, then this would not be memoryless dependence. This would be memory-based dependence. So to highlight the need of memoryless dependence, imagine that we are given that x1, x2 till xn minus 1, the variables that have happened and have taken some values. So all these previous history is available to us. And we are interested in calculating x of n, which is the next state. So now we are making a big assumption that all of this history is available with us. And this would make things very hard. Would it not be very nice if we could just forget all of the history and just decide on the basis of the current state? So if that was possible, we could have replaced this conditional distribution by just f of xn, given that xn minus 1 has happened, because all of the previous states do not affect the future. Xn minus 1 is the current state. We have forgotten all of the history. The next state is just a function of where we are at currently. So this would be very nice to have, because this makes things very easy for us. Because now we can use the relationship that this conditional probability is the ratio of the joint probability and the marginal probability. And with that, we can calculate many interesting things. We can calculate the joint distribution as the product of the marginal and conditional distribution. So if we were to ask what is the probability of xn minus 1 happening at the n minus 1th observation and it being followed by a value of xn, if we want to ask this question, we can simply answer it by saying, okay, let's first see the marginal probability. Where is the process at the current state? That is modeled by f of xn minus 1. And then we simply have a conditional distribution that is dependent on just one value, which is the current state. So this makes life very easy for us. So as mentioned before, a stochastic process to be completely described has to be described by a joint distribution. But if we have this memoryless dependence, the calculation of this joint distribution becomes very easy. So how was this memoryless dependence proposed? So this was proposed in the earlier 20th century by Andrei Markov, who was a Russian mathematician who proposed a process in which the future of a process is only affected by the state of that process at that given time. So any history does not affect the future. And this property is known as the Markov property. And the processes, the stochastic processes that have this Markov property are known as Markov processes. And we would see that almost all of the elementary stochastic theory deals with just Markov processes, because it is very hard to work with more complex stochastic processes. It just becomes too much messy. But if we have the Markov property, it becomes easier to manage. So Markov property, if I have to repeat, allows us to calculate the joint probability of multiple random variables as products of the marginal distribution and conditional distribution. So if we were interested in calculating the probability of a sequence x1 till xn minus 1 till xn, we could simply calculate the probability of the first instance taking value x1. And then from there onwards is just conditional probabilities. And these conditional probabilities are simple because of the Markov property. It is just conditioned on the current state. All the previous history is forgotten, and that really simplifies our analysis. So almost all of the processes that we would be covering in this course would be some variant of this Markov process. So let me now get into the part of this lecture where I talk about common stochastic processes. And we're going to focus on the processes that are Markovian. The reason is that independent IID processes are not very appealing because they cannot model the dependence that is seen in empirical processes. And if we go into too much detail and if we make the model very complex, then we are not interested in following it up because it becomes very difficult to analyze mathematically. But if we have the Markov property, then things are easy. So let me explain a Markov process through an analogy. If we have a Markov process in which there are discrete number of states, we refer to such a process as a Markov chain. And for the remainder of this course, we would actually be focusing on Markov chains only. And for the study of network performance evaluation, Markov chains are most important, in which the states are discrete. But they may be continuous time or discrete time. So for this analogy, we're going to make things simple. We're going to talk of discrete time. So this is an interesting example. You can imagine a frog in a lily pond, and there are these lily pads. So again, to make things simple, we have just 3 pads, and the frog is currently on the pad number 1. So we number each one of these states, and we place a restriction. We say that at every tick of the clock, the frog has to make a transition. It has to go to some other state or possibly to the same state, but it has to make a transition at every time tick, and we know the probability of these transitions. We know with what probability it would go from 1 to 2, from 1 to 3, and from 1 to 1. In discrete time Markov chains, we can make use of these probabilities. We would see that in continuous time Markov chains, these probabilities will not work, because in continuous time, you can move at any given time. So in a sense, you would have infinitesimally small intervals in which you can make the transition. And the probabilities for making a transition in these very small intervals is very small. A more natural way is to express this in terms of rates. So we would say that the average rate from 1 to 2 is this. So for continuous time, we use rates to express the transition chances, and in discrete time, we make use of probabilities. So now we have a very graphical example in front of us, and this is how things work. In a stochastic process, the process evolves in time. So it may be in some value at some time, it may take another state at another time. So if you have discrete number of states, it would be in some state at any given time, and usually we have a restriction that every time tick or at every observation, we have to make a transition. So in this case, the frog would jump around, and then we can ask many interesting questions about this. If we have the restriction that we have memoryless jumping, which is that if you are in state 1, you are still going to go to the other states with the same probability regardless of the previous trajectory. It does not matter what path you've taken to reach the current state, the history is forgotten. So an important point here is that the future state depends on the history. It's not as if we forget all of the history. We do, the future state is dependent on the history, but only through the current state. In other words, still, the current state captures all of the history. So we don't have to memorize the history. The position that you are at is all the information that we need. So if we have such a frog in a lily pond environment, and we want to answer questions like, okay, what is the probability that the frog would be on lily pad 3 at any given time that I observe? This can be observed if we know the steady state distribution. If we observe this for long enough, then we can estimate that what is the state distribution of this chain, which tells us that, okay, it could be that the frog is at state 1 25% of the time, it is at state 2 50% of the time, it is at state 3 25% of the time. This is very useful for us in many cases. I will come to shortly. So if I want to characterize a chain that is modeling this process, I can use a matrix known as P, in which I'm listing the probability from every state to every other state. So because there are 3 states here, we would have a 3 by 3 matrix, and we have some sample values given. So let's say the probability of going from 1 to 1 is half. The probability of going from 1 to 2 is 1/4. The probability of going from 1 to 3 is 1/4 again. So if you have observed this carefully, you would note that the probability matrix is summing to 1 in every row. This is because we have the condition that there has to be a transition at every time instance. So because of that, we have to go somewhere. So in this case, 1 tells us that it stays in the same state if it is in state 1 half of the time, and it goes to the other states half of the time. Also, if you observe, the sum is 1, which tells us that it is going to go somewhere and it is not going to drown in the water. It will be on some lily pad. So this is another assumption that we have, that in a stochastic matrix, which is this matrix is known as a stochastic matrix, if we sum all the values in a row, we would get a value of 1, which intuitively tells us that you have to make a transition and go somewhere. So we may ask, if we're interested a lot in how frogs move around in a lily pond, we may ask ourselves that, okay, what is the distribution of being in particular states? And Markov chain lets us answer such a question. It can also answer other questions, like one thing that we've studied is the long run state distribution of the system being modeled. In this case, it was at which state are you in? So this is very useful in many different contexts. So for example, you have a Markov chain which is modeling the weather. So the weather may be rainy or it may not be rainy. So if we can estimate the steady state behavior of being in the rainy state, then umbrella manufacturer would be very interested in this, because he can estimate the amount of umbrellas he has to make on the basis of this information. A bank manager may be interested in modeling the arrival of work to his bank clerks, and the state in which there are no customers would indicate to the bank manager that what proportion of the time are the bank tellers idle. So it depends on the things that you want to model, and accordingly, once we have the steady state information, we can use it for planning. We can also answer questions like, okay, if we allow for 5 transitions, where will we be next? So this is known as an n-step transition probability. In the example I gave, n would be 5. So this would be a 5-step transition probability. After 5 observations, where do you expect to be? And you can have a distribution for that. If you have a model in which you're going to come back to your state again and again, we would see that such a state is known as a recurrent state. Then we can talk about the first passage time, that how much time would it take to hit some state A. So we may be interested, if we've modeled a system in which it's important to get to a certain state, we may answer for this probabilistic stochastic process, which is random, we may give a mathematical answer that this is the expected value for this. We can also talk of a mean absorption time. In Markov chains, we can have a state in which you can have incoming transitions, but the outgoing transition are always back to the same state, and such a state is known as an absorbing state. So we may be interested in a chain that what is the time it takes to get to the absorbing state. So these are some of the questions we can answer with a Markov chain. The frog in a lily pond example that we saw was a discrete time Markov chain, and we've seen that to characterize such a Markov chain, we can make use of the P matrix, in which we are specifying the transition probabilities from every state to every other state. In general, in discrete time Markov chains, the transitions occur at fixed times, and if even they may be at irregular times, but they are predetermined. So that is the characteristic feature of discrete time Markov chains, that the times of transitions are predetermined. In general, the probability transition matrix may be a function of time as well, because let me reiterate the Markov property. The Markov property was that the future trajectory of the process is dependent only on the current state. It does not limit the transition probabilities to change in time. So in the future, it may be that if you are in the same state, the transition probabilities would change. The future state is still dependent only on the current state, but the transition probabilities may change with time. If that is happening, we would say that this is a process that is not time homogeneous. Time homogeneous Markov chains are those in which the probability transition matrix is invariant to time. It does not change with time. And for our study, we would be mainly concerning ourselves with time homogeneous Markov chains, unless it is stated explicitly. In continuous time Markov chains, as mentioned earlier, we cannot use probabilities because the transition can take place at any possible time. So there are infinite number of departure points. Accordingly, a more natural way is to make use of transition rate, which we define as if the transition rate from I to j is specified as Qij, and it is the limiting form of Pij, which is the transition probability from I to j. And if we have the transition rates to all the states, then we have the Q matrix. In this case, usually we do not have a self loop. So Q11 is actually just the negative of all the outgoing rates. And we would cover this when we talk of the solution of continuous time Markov chains. That is not the subject of today's session. Currently, I'm just introducing, generally speaking, continuous time Markov chains. But it must be pointed out that Q11 or all the rates back to itself are negative values, that the value of which is equal to the sum of all the outgoing rates. This will become apparent when we see this in much more detail later on. Okay, another important point is that the state sojourn time, or the time you spend in a state, is represented by an exponential distribution. And this follows from the memoryless property of Markov chain. In a continuous time Markov chain, you can move out at any given time. In other words, at every infinitesimally small time, you can move out. So we can think of moving out as a success and staying there as a failure. And the distribution of the first success, the continuous time counterpart of the geometric variable, is the exponential distribution, which tells us the time we expect before we move on to some other state. So now we come to the part where I give you a broad overview of all stochastic processes, and we are going to mainly talk of generalizations of the Markov processes and special cases of Markov process. This follows from the book Queuing Theory by Leonard Kleinrock, Volume 1. So if you're interested, you can also look up that book to find the source of this taxonomy and this description. In a Markov process, in general, we are limited to have a memoryless sojourn distribution. यानी कितनी देर आप एक स्टेट में रहते हैं, it must be memoryless. If you have a discrete time Markov chain, this then has to be the geometric distribution, because geometric distribution is the only memoryless discrete distribution. If we have a continuous time Markov chain, it has to be an exponential distribution. However, these are stringent requirements. If we want to relax this and we allow the sojourn time to be from an arbitrary distribution, we would have a generalization of the Markov chain or the Markov process. This is because for it to be truly Markov, the sojourn time has to be exponential or geometric. But let's say at the point of making a transition, we have the Markov property that, okay, the sojourn time is arbitrarily distributed, but now it's the time to make a transition. Do we have the Markov property now? If you have the Markov property in which the future state is dependent only on the current state, but you have this arbitrary sojourn time, you have what is known as a semi-Markov process, in which the Pij may be arbitrary, you can move to any other state, but the sojourn time is, the distribution is arbitrary. It is not necessarily memoryless. A special case of the semi-Markov process is the Markov process, in which you have the sojourn time is memoryless, and also you can move from any state to any other state. The future state is only dependent on your current state, and we can calculate on the basis of transition probabilities. Okay, so this is the special case of semi-Markov, which is the Markov process. And then we can talk of a random walk. A random walk is a special case of the semi-Markov process. In a random walk, we're interested in tracing the trajectory of a particle in some space. Or we can say that we have a time process and it moves around. At every given time, it adds a certain random variable to its point, and we have the next state. In this, the distribution of sojourn time or the time till the next transition can be arbitrary, and accordingly a random walk may be Markov or it may be semi-Markov. If it has the exponential or the geometric distribution, it may be Markov. In other cases, it would be semi-Markov. A special case of random walk is the renewal process, in which instead of tracing the path taken by a particle across some space or time, we're interested in the number of transitions. So if we are talking about the number of transitions counted until certain time, this would be a renewal process. The time between successive events can be arbitrary. And if you are able to relate things, you would be able to make out, we earlier talked of a Poisson process as a counting process, in which the distribution is exponential. And because of that, Poisson distribution is a special case of the renewal process. Okay, now we come to the basis of queuing theory, the birth-death process, which is a special case of the Markov process. This is an even simplified form of the Markov process, in which you can only make transitions to the next or the below state. So you can only talk to your neighboring state. And the sojourn time is also memoryless. Therefore, the birth-death process is a Markov process. And now we come to the crown jewel of all the stochastic processes, the process which is at the intersection of all these processes, the Poisson process. A Poisson process is a Markov process. The distribution between successive arrivals is exponential, and the next state is only a function of the current state. It is also a renewal process in which we are counting the number of events that have taken place. It is also a special case of semi-Markov process, because any Markov process is a special case of semi-Markov process. So you can see that it holds a very central place. We also can classify a Poisson process as a birth-death process in which we have no deaths. You only have arrivals coming in and there are no deaths. So this is a special case of birth-death process. And a special characteristic of the Poisson process is that not only is this just a pure birth process, but the rate of birth is also constant. So regardless of which state you are in, you're still going to arrive at the same rate. Every state has the same transition rates. So this is very interesting, and this highlights why Poisson process is central to the study of stochastic processes, and we would use it extensively in our study of network performance evaluation. In the end, I would like to talk about stochastic models and how they may or may not approximate reality. So when we are talking about stochastic processes, we are essentially talking about the properties of models. So the memoryless property is a property of the model, not necessarily of the data or the empirical process that we are trying to model. And these are two different things. You may say that the model is memoryless, but it is very hard to prove that the empirical process is memoryless. Accordingly, it is very instructive and probably worthwhile to recall the quote I've already stated in the lectures on the art of modeling by George Box, that all models are wrong, some are useful. So we need to take care of our assumptions, and we need to see if the assumptions match with the reality. So with this, I would now like to conclude this lecture. We've talked about Markov processes today, and we've seen that they are very simple models of empirical processes in which the future state is just dependent on the current state. And we've seen that a Markov process is flexible enough and powerful enough to model many practical processes of interest in finance, engineering, and in many other fields. And it is also simple enough for mathematicians and engineers to work with this and come up with clean, tractable forms of solutions. We would continue our discussion on stochastic processes, and we would talk in the next session about solutions of Markov chains. So till then, Assalamu alaikum wa rahmatullah.